Can you imagine a time when the universe was sweltering hot, dense, and full of energy? A moment when the very space expanded at such incredible speeds that galaxies started moving away from us, faster and faster the farther they were. This expansion implies that once upon a time, everything in the universe was closer together. But that's not where the story starts. In fact, the universe as we know it was born from an inflationary period that existed before the Big Bang. Can you believe it? In this period of cosmic inflation, the universe was utterly empty, no particles, no matter, not even a single photon. Yet, the empty space fluctuated with energy. As the universe expanded, these fluctuations stretched out, and new ones were created. And then, suddenly, inflation ends, giving birth to new universes. Now, picture our universe, born from one of these regions about 13.8 billion years ago. When inflation ended, a hot Big Bang began, converting energy into matter and radiation. The universe quickly filled with particles, antiparticles, and radiation, creating a soupy mix as it expanded further. Soon after, the universe cooled down, and particles started interacting, forming the cosmic web of stars and galaxies we observe today. But here's the catch. Something else happened, something utterly mind-boggling, something that... well, you'll find out soon enough. What's up, my amazing and curious folks? Are you ready to unravel the mysteries of the universe with us today? I'm your host, Caesar, and with me is the vibrant and intuitive Sonia.
Hey there, folks. Can't wait to dive into today's curiosity with you all.
You're tuned in to the Curiosity Wonderland, your daily stop for all things curious and intriguing. Don't forget to hit subscribe and the bell icon so you never miss an episode with us. Stay tuned, folks, as we bring the cosmos right to your speakers. So, let's dive back into the early universe, when things were really heating up. As we observe galaxies today, we notice an intriguing pattern: the farther a galaxy is from us, the faster it seems to move away. It's as if the universe is expanding, with galaxies and clusters getting more and more distant from each other over time. If we reverse this process, winding back the cosmic clock, we find that in the past, the universe was hotter, denser, and everything in it was closer together. Imagine, if you will, a time before the first galaxies formed, before the first stars ignited, even before neutral atoms or atomic nuclei, or even stable matter, could exist. The earliest moment at which we can describe our universe as hot, dense, and uniformly full of stuff is known as the Big Bang. When we look out into the universe, we don't just see stars and galaxies as they are now. We also see them as they were in the distant past. The farther away we look, the farther back in time we're seeing. The universe at these distant vantage points appears less structured, hotter, younger, and less evolved. Now, I know some of you might be getting confused. You might be thinking, isn't the Big Bang the birth of time and space? Well, at one point, that's how cosmologists thought of the Big Bang. If you take something that's expanding, like our universe, and go back in time, it becomes smaller and denser. The idea was that if you went back far enough, everything, all matter and energy, would converge to a single point, an event known as a singularity. This was seen as the birth of space and time. But our understanding of the universe has evolved, leading to new and exciting perspectives. Shall we delve into that? So, let's delve a little deeper into what we know today, in the year of 2023. There's a wealth of evidence suggesting a non-singular origin to our universe. This means that the universe didn't start from a single point or a singularity. Instead, it's best explained by an inflationary period that occurred before the Big Bang, and the Big Bang itself is the aftermath of the end of this inflation. Now, this period of inflation predicts that a series of independent universes will be spawned, each one completely disconnected from the others, separated by ever-inflating space. One of these bubbles, where inflation ended, is thought to have given birth to our universe around 13.8 billion years ago. During this inflationary period, the universe was completely empty. There were no particles, no matter, not even photons, just empty space with a vast amount of energy at every location. This energy fluctuated over time, at a rate of about 1 part in 30,000 on average. With the universe expanding in a rapid, relentless fashion, these fluctuations were stretched to larger scales while new, small-scale fluctuations were created. This layering of fluctuations is one of the defining predictive features of cosmic inflation. But inflation didn't end everywhere at once. It came to an end randomly in different locations. If you could have observed this, you would have seen a nearby region where inflation ended, and the space between you and that region would have expanded exponentially. For a split second, you might have been able to glimpse the start of a Big Bang before that region disappeared entirely from view. As I delve into this world of cosmic curiosities, it's just mind-boggling. We live in a universe that's constantly expanding, where the laws of physics as we know them had a beginning. It's wild, isn't it? I'd love to hear your thoughts. Are you enjoying this deep dive into the universe's beginnings as much as I am? Remember to hit the like button and share your thoughts in the comments, folks. Let's continue this cosmic journey together. Now, let's imagine a relatively small region, perhaps no bigger than a human-sized hamster ball. In this small cosmic space, the energy inherent to space transforms into matter and radiation. This conversion process is incredibly fast, taking approximately 10 to the power of -33 seconds. Although brief, it's not instantaneous. As this energy morphs into particles, antiparticles, photons, and more, the temperature skyrockets from just a few degrees above absolute zero to perhaps 10 to the power of 20 degrees Kelvin. With such a huge amount of energy, everything will be moving close to the speed of light. All these quantum particles will behave like radiation due to their immense kinetic energy. This conversion process, known as reheating, signifies the end of inflation and the beginning of what we know as the hot Big Bang. The transition from the energy of inflation to matter and radiation represents a drastic change in the universe's expansion and properties. It's like when a ball sliding on a high surface suddenly crumbles and releases energy. This signifies the end of inflation and marks a huge increase in entropy wherever inflation ends. Now, during the inflationary period, space expanded exponentially, with distant regions accelerating away. But as inflation ended and the Big Bang commenced, the expansion slowed. More distant regions began receding more slowly. So, in an inflationary universe, the distance to any object would double after a certain time, and then double again and again in a relentless pattern. But once the Big Bang began, the expansion of the universe immediately slowed down. Imagine, in the very young universe, at high temperatures, not only could particles and photons be spontaneously created but also antiparticles and unstable particles. This resulted in a primordial soup of particles and antiparticles. It's amazing, isn't it? To think about how our universe transitioned from an empty, inflating space to a dynamic, expanding cosmos filled with matter and radiation. Each step in this cosmic journey adds another layer to our understanding of the universe. What do you think? Do you find this as fascinating as I do? So, as this cosmic soup swells, only a few specific particles can form. And within a few seconds, the universe is much larger than its earliest stages. As it expands, the density, temperature, and expansion rate all rapidly drop.
That's intense. So, in simple terms, we're saying that from an area of inflating space, you'd witness inflation ending around you many times, right?
Exactly. Those areas where inflation ends quickly fill up with matter, antimatter, and radiation and move at a slower pace compared to areas still inflating. This gives the impression of being in a typical region dominating spacetime's volume.
That's wild. And these areas where hot Big Bangs take place, they're expanding away from all the other locations where inflation still goes on?
That's right, they recede from one another quite rapidly due to the change in expansion rate. In the standard inflationary picture, there's virtually no chance that any two universes, where separate hot Big Bangs occur, will ever collide or interact.
So this is where the idea of a multiverse comes from?
You've got it. That's exactly where the scientific motivation for a multiverse stems from. Inflation doesn't end everywhere at once, it ends in distinct, independent areas separated by space that continues to inflate.
And the universe doesn't expand into anything, it itself is expanding, correct?
Precisely. The universe itself is expanding. Now, let's talk about our own cosmic luck. In the region where we exist, inflation came to an end. The energy inherent to space transformed into a hot, dense sea of particles. The only imperfections, the only departures from uniformity, relate to the quantum fluctuations that existed during inflation.
So, this means that these quantum fluctuations ultimately led to the structure of our universe?
Yes, exactly. These fluctuations created regions with varying density. The positive energy quantum fluctuations led to initially overdense regions, while the negative energy fluctuations resulted in initially underdense regions. Despite the differences being minimal, they were enough to serve as the seeds for cosmic structure. denser regions created larger gravitational potential wells, making the light from those regions appear colder. In contrast, underdense regions appeared as hotspots, with regions of average density having average temperatures. Now, it's important to note that we can't observe these density fluctuations as they were when the universe first underwent the hot Big Bang. There are no visual signatures from that era that we can access. The first visual evidence we have comes from 380,000 years later, after countless interactions had already taken place. However, even with that limitation, we can extrapolate what the initial density fluctuations were. And what we find is a story that lines up perfectly with cosmic inflation. The temperature fluctuations in the first picture of the universe, the cosmic microwave background, validate the way the Big Bang began. These fluctuations are based on primordial ripples produced by inflation. The flat part on large scales has no explanation without inflation. This flat line represents the seeds from which the Pecan Valley pattern emerged over, again, those first 380,000 years of the universe's life. Now, what might be observable to us in the future are the gravitational waves left over from the end of inflation and the start of the hot Big Bang. Unlike visual signatures, gravitational waves are never slowed down by interactions. They speed across the universe at light speed, washing over us from every direction. To truly understand how our universe got its start, our task is to find a way to observe these waves, either directly or indirectly. Various ideas and experiments are being tested, but so far, none have been successful. We know what the spectrum of these fluctuations will look like and their impact on the light within our universe, but we're not sure about their magnitude. Various models of inflation make different predictions. Only by eventually measuring these waves can we determine which model accurately describes our universe. What do you think? After inflation ends, the energy inherent to space itself transforms into particles, antiparticles, photons, and so on. All the universe can do at this point is expand and cool. There's a constant flurry of activity with particles smashing into each other. Sometimes this leads to new particle and antiparticle pairs, sometimes pairs are annihilated back into photons or other particles, but always dropping in energy as the universe expands. It's important to note that the universe never reaches infinitely high temperatures or densities, but it does attain energies that are perhaps 1 trillion times greater than anything we could produce with the Large Hadron Collider. And these tiny seed overdensities and underdensities we've been talking about? They eventually grow into the cosmic web of stars and galaxies that exist today. 13.8 billion years ago, the universe as we know it had its beginning, and everything that's happened since is part of our cosmic history. So, to put it all together, our universe started off as a hot, dense, and energy-filled entity. It expanded rapidly during a phase we call inflation, stretching cosmic fluctuations while creating new ones. When inflation ended, these energy fluctuations transformed into particles and radiation, marking the start of the hot Big Bang. As the universe expanded, the density and temperature dropped, giving birth to the cosmos we see today. The mystery of our universe's beginning, it seems, is not a singularity, but a dance of inflation and energy conversion that gave rise to everything we know. And if you're looking for a punchline to this cosmic tale, here it is: the universe didn't start with a bang, but with a stretch.
What a fascinating journey through cosmic history we've taken today, folks. It's amazing to think that our existence, and everything we can observe, started from these tiny fluctuations during inflation. Thank you all for joining us in unraveling this cosmic mystery. If you've enjoyed this episode of Curiosity Wonderland, don't forget to blast that like button, leave us a comment, and share it with your friends.
Absolutely, and remember, the universe is full of mysteries waiting to be discovered, so keep looking up and keep questioning.
That's all for today's episode of Curiosity Wonderland. Stay curious, and until next time. Caesar and Sonia, goodbye.
Today's discussion was inspired by an article titled "What Was It Like at the Beginning of the Big Bang?" by Ethan Siegel, which I found on the Big Think site, published on November 20th, 2023. The full URL will be in the description if you're curious to read more. Until next time, folks.